Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay. Oh. Alrighty. Welcome all along this week. Oh, that's very loud. Turn that down a little bit. Better? Okay. All right, thanks for your patience. Okay, so just to recap a couple of things. So assignment due on the 22nd, yeah? Today's the 20th, so a couple more days to go. The questions I always get asked by email is when is it due? Noon, okay? So just pop it in the box. So if you go up to the 4th floor of the main building, 26C, and you'll find the assignment box. So you're supposed to have it in there by 12 noon. I think they clear it out shortly after that, 12:30. No one's going to be standing there, at least I'm not going to be standing there looking at my watch second by second. So if you're a couple of minutes late, I don't care, it's not a problem. If you have a problem, like if you're unwell or whatever happens, just let me know and we can sort something out, okay? So that's thing one. Thing two, again, this is just mainly to repeat some of the things that I mentioned at the beginning of last Monday's lecture, because I'm getting emails about it still. So again, what do I expect? 4-page report, can't be longer than 4 pages, cover page doesn't count. So you've got a cover page which you can download off the web. No, you don't have to put your name on it. In fact, you shouldn't put your name on it. One thing I will ask you though is when you put your student number on it, please write it clearly. Last year I had to do some detective work because I couldn't read the number and I had to work out what on earth it said. So we did work it out in the end by process of elimination, but you don't want that happening to you, right? So please write your number as clearly as you can on your assignment. If you want to, as well as writing it on the cover page, you can write it on every page, just in case, the staple fails or whatever. Okay, so there's that. I won't read past 4 pages, so no point going past 4 pages. Now, the other question that I got about 7 or 8 people asked me the same question, which is something I talked about last Monday, so I'm going to say it again. You've got 8 groups, okay? The groups are in descending order of pitch. So soprano 1 is higher pitch than soprano 2, okay? That does not mean you can't group the data. Grouping the data might be a useful strategy, but it is what it is, right? The data is in descending order of pitch, okay? So I just want to clarify that because I literally got, it must have been a dozen emails asking me exactly that question, okay? And I did talk about it last Monday. So my response is, yes, please go and listen to Monday's lecture, okay? So, all right, what else? That's about it. Some people have emailed me asking me questions about how to use ggplot. Use it if you want, but I'm not going to answer questions about it. It's not what we're doing in this class. It's not that I'm being mean or anything, I just don't know the answers in a lot of cases. I'd have to do exactly what you'd have to do, which is Google it. Right? So I don't use ggplot. So, well, someone wrote me a nice little opinion that ggplot is much prettier than R. Yeah, I don't agree. So I think it's ugly, but anyway, you can use it if you want, but if you do use it, I can't necessarily help you do finer point things in it. I can do the basic things, but if you're asking me how to do finer point things, I'm just going to have to look it up like you. So anyway. All right, where are we? So we've been talking about applying transformations to straighten up scatter plots. I wanted to continue talking about that today, and I wanted to just show you some examples. So this is our very familiar by now rat data, and you can see there's the original data in the top left here. You can see it curves upwards, all right, but it's got that heteroscedasticity. So it's got that non-constant variance, skinny at one end, fat at the other. The second plot is a plot of x versus square root of y, and the reason that you might transform y instead of x is that that variation was out of control initially, and transforming y, which is a vertical ordinate, is really the only way you're going to seriously mess with that variation, okay? And you can see it straightens it up a little bit, but the variation is still going a little bit nasty as you move from left to right, and the curvature's still there, roughly speaking. This is x versus log y, so this is what we think might be the right answer. You can see fairly linear, and the variation is fixed, pretty much. Now, I took it one extra step, a stronger transformation than log, and we'll talk about why that is in a second. And you can see, so this is against minus 1 on y. Okay, so that's y to the minus 1. So we're, again, looking at powers of x and of y, and here the power of y is minus 1. You might say, why is the negative sign in front of it? It's to preserve the order, or preserve the direction of the plot. Because, you know, you remember how inequalities work? If A is less than B, if you flip them, take inverses, the inequality switches. In other words, the direction of the curve would switch. So to push that direction back so it's going sort of that way is the negative sign is here. And you can see what happens. It's really interesting. You actually get a curve but in the other direction, okay? So it was curving sort of concave up, and now it's curving concave down. And you'll notice that the variation which was in control here has gone out of control again, but in the other direction. It's fat down this end and skinny up that end, okay? And the reason I wanted to show you that plot was that you've got available to you all of these different transformations, and they're all of differing strengths, but it actually works in a really simple way. So I'm going to switch now to the document camera and just show you the different shapes and how you might remediate them. So I'll zoom in if I can. So this is the first shape. So this is what our data looked like initially. And the game here is, so you've got data that sort of follows the solid line, but what you'd really like to see is that dotted line. You'd really like to see a straight line. So our remedy to this has been to transform this original data in a way that straightens up that scatter plot. Now, there's a very simple way to think of this. Think of the solid line as a rope that's got two ends, okay? And you're allowed to pull the ends of this rope either horizontally, that is in the x direction, or vertically, that is in the y direction. Now, if I said to you, I want you to pull one or both ends of this rope in order to straighten that rope out, then the natural thing to do would be to grab this end and maybe pull it that way, and or grab this end and pull it that way. So in other words, pull it up in the horizontal direction or pull it down in the vertical direction. Okay? So either up in the horizontal direction or down in the vertical direction. Now, I'm just going to wander down the page here, and we're going to try and summarise this in a way that's easy to remember. So I'm going to think of this as a ladder. Let me centre this for you. And in the middle of this ladder, I've got power 0. Power 0. There we go, power 0. Okay? Sorry, I should say power 1. Oops. Ah, bugger. Power 1. because power 1 means do nothing, right? Right, so this is x to the power 1. This is just your original data. This is y to the power 1. Okay? Then I can imagine this being a ladder. Okay, so it's got rungs above and below the sort of do nothing rung. So this one here might be x to the power 1/2, because 1/2 is less than 1. As I go further down, x to the power 1/3, x to the power 0. For this I'd use log, and so on. If I keep sliding on down, I get x to the minus 1/2 and so on. Same thing with the y's. I'd go from y to square root of y, cube root of y, etc. Okay, all the way down. And if I decided to go up the ladder, then x squared, y squared, x cubed, and y cubed, and so on. And I can use any power of 1. I'm sticking to the sort of obvious ones, like, halves and thirds and squares and cubes. But, if you wanted to, you could put x to the power pi if you wanted to. I mean, people would look at you as if there was something seriously wrong with you, but you can do it. Now, you might ask, well, why do you stick to the integer powers and the half powers and things like that? Well, it's really, you should use whatever works well, right? But it seems to me, at least from looking at lots and lots of data over time, that God doesn't do weird things, like make x to the power pi the answer, right? Squares work. Square roots work, logs work. There's often good theory behind that. Logarithmic models, for example, are about additivity versus multiplicativity. Is that a word? Probably. Okay. All right, so looking at this ladder, I'm just going to see if I can zoom back in a bit so you can see the whole thing. There we go. So from the do nothing rung, this is the do nothing rung, leave the data alone, you can think about moving up the ladder, or you can think about moving down the ladder. Oops, down the ladder. Okay, you think about moving up or down. And so this is how we're going to conceptualise straightening our picture. Okay, so if we come back to the original one here, if I'm going to take this and think of it as a rope and I'm just going to pull the ends of the rope, I could either go up the ladder in the x side, or I could go down the ladder on the y side. So that would suggest maybe x goes to x squared. And down the ladder on the y side, you'd think, well, that's like y goes to square root of y, or y goes to log of y. These are the things that are suggested by my little physical analogy that this thing's a rope that you can pull, right? And so you could transform x to x squared, you could transform y to square root y, y to log y. And then we've got that piece of added information that we talked about last week, which is, which one do you do? Well, if there was no variation here, it wouldn't matter which one you did, because x squared and square root of y are inverse transformations. They do the same thing. But in the presence of heteroscedasticity or homoscedasticity, you're going to choose whichever one gives you the variance relationship you want at the end. So with this picture here where it's curving sort of that way up, you could take x to x squared, but that's not going to mess with y. And so if your data exhibited non-constant variance at the beginning, it's going to exhibit non-constant variance after transformation as well, because you didn't mess with y. And so you don't want that. You want to mess with y in this case. So you'd choose to take y to square root of y or y to log y in order to fix this one. And you can try until you get it right. This is empiricism, okay? This is try something, see if it works. If it doesn't, use the information that you gained by trying that first thing and try something else. So, for example, if I switch back to the graphic that we have, there's my original data. You can see it's curved upwards, right? So I know if I look at that curve, I'm either going to go x to x squared or cubed or whatever, or y to square root of y, y to log y. Okay? So I try something. I try y to square root of y. And if you do that, you see my problem's not quite solved. Now, it's still curved up. So the suggestion would be, essentially, you didn't pull the rope hard enough. Okay? So I went from y to square root y, and it straightened it a little bit, but not enough. So I had to pull harder. What does pull harder mean? It means go down the ladder further. Okay? So what's further down than square root? Well, cube root. I could try that. Make a judgment. Have I pulled the rope hard enough? No, turns out. Go down to the 0 rung, which is log. Have I pulled the rope hard enough? Probably looks okay. The reason I show you this one is, if you pull too hard, you basically pull it through the straight line and out the other side. So instead of curving up, it curves down. So the physical analogy works really well in terms of thinking about how hard you have to pull this scatter plot around so that you straighten it up. Okay? And you can play this game with every one of the shapes that we have. So if I shift across here to this shape here and zoom in a bit, isn't this fun? There we go. Again, I want to be on the straight line. I'm here, so I'd either do that or that. So I'd either go up in the y side or down on the x side. Okay? So down in the x side means take x to square root of x, for example. Up on the y side, take y to y squared, for example. Okay? And again, it's going to depend, which one you mess with is going to depend on the spread characteristics. Okay? It's going to depend on the spread characteristics. And we're going to look at an example in a minute. I'll show you how that's going to work. Okay? So hold that thought. Again, try something. It's like pulling the rope. If you pull it not hard enough, you'll need to continue to go in that direction on that ladder. If you pull it too hard, you've got to pull back. Okay, same game can be played with each of these two here. So let me do these both at once because, okay, so this one here, you're either going to go up vertically, which is up on the y side, or up horizontally, that's up on the x side. So y to y squared, x to x squared. Remember, this thing looks like a quadrant of a circle, which is x squared plus y squared equals c squared, so you might have to do both. Okay, this final one, down on the x side and or down on the y side. Okay? And so each of these four shapes, you can come up with at least a set of recommendations of what you would need to do in order to try and straighten up this scatter plot. Okay? So you've got a set of possibilities. Now, yep.
Is it possible that omega play around with both?
Yes, and I'll show you in a second how that might work. Absolutely. So the bottom line is when you see something that's not straight, as long as it's a simple curve, and let's face it, if you've got a complicated looking curve, you've got much fewer choices. Right? If you've got a complicated looking curve, you're basically betting on being able to recognise the functional form and then hopefully being able to fit that. You know, you're probably out of luck unless you've got some theory in behind. Okay? And look, there are theoretical models that are available in some circumstances, but to a statistician, you look at the data and you let the data kind of drive what you do, you're not necessarily going to have that support. Otherwise, you try things and then you try and see whether those shapes have any sort of theoretical support. So, let's go and have a look at, very quickly, let's have a look at another set of data. So this data is called Raptor. Okay, so it's a big old data set. It's scroll all the way up here. So what it is it's, most people have seen Jurassic Park, so they think raptors are dinosaurs, but raptor itself is a bird of prey, so an eagle or a hawk. Turns out there are hundreds and hundreds of different kinds of birds of prey, and this is data from the ANU. So these are the names of the birds, and they've got lots of data on each of the birds. They've got female, the weight of the female, the weight of the male, the length of the egg, the breadth of the egg, and what else? Lots of stuff. The clutch size, so the number of eggs that typically are produced, something called dimorphism, and something called egg volume. Right? So the first column is female weight, last column is egg volume. We're going to look at those two columns. All right? So I'm going to show you the initial plot. So I'm just going to go x equals raptor first column. So that's the female weight. And y equals raptor seventh column. That's the egg volume. Okay? And I'm going to plot xy, and we'll have a look at the initial scatter plot. Okay, so this is female weight on the x-axis, egg volume on the y-axis. All right. Okay, so what's the shape? Yep. So it sort of starts off pretty steeply and then shallows out. Okay, so that's pretty cool. It's one of our four shapes, so that's cool. Okay. Now, let's think briefly about the heteroscedasticity problem. Is it homoscedastic? No, clearly not, right? Skinny down this end, right? Wide out that end, okay? Again, you can play with lines low s of x and y. I've got to put the word low s in, don't I? Low s, x and y. Something failed here, which is interesting. It's basically joining the dots. It's using a window width that's too small. I believe this is because this data set has some missing data. Okay. If I do sum of is.na, so how many missing in x, there's nothing missing in x. If I do it for y, there's two things missing in y. Right? So they've got the weights of all the females, but they're missing two egg volumes. What do you reckon happened? Eggs broke. What are you going to do, right? You've all been to the supermarket and opened the packet and there's two broken. Don't buy that packet. Okay? So I think I have to force... I think I can do this by saying x for which not is.na y and y not is dot na y. So what I'm doing is I'm just clearing out the missings and see it fixes it. Okay, so plot xy. Okay, so there's a little bit of new s plus in, new r in here. I'm trying to subset the data a little bit. Low s originally had a problem. Generally speaking, when a function does something funny, then it's usually because there's missing values in your data, right? So that was my hint. So I had to work out first how many missing values there are. So is.na produces a true when something's missing and a false otherwise. And if I add those up, if I sum them, trues get added in, falses get ignored. So there were two trues in that big long vector, okay? So this told me that I've got some y's missing, but I don't have any x's missing. So what I want to do is I want to pick out the x's for which y is missing, and I want to only use the ones for which y is available. So this exclamation point here reverses the trues and falses. So is.nay says true when y is present, and true when y is missing and false when y is present. This exclamation point reverses that. So true when y is present, false when y is missing. And so it only picks out those. Okay, so there's my low S curve. Looks pretty cool. All right, so what I'm going to do now is I'm going to try and straighten up this scatter plot. So let's think about how we might do this. So it's this shape. Okay, it's that shape. So let's quickly dash back over here. and focus in. So it's that shape. So if I wanted to straighten it, I could either go down in the x direction or up in the y direction. Okay? Or both. Okay? Down in the x. So x could go to square root x or log x, something like that. Y could go to y squared or something like that. Okay? Now come back and look here. All right. Heteroscedasticity is present, right? So it's skinny at one end, fat at the other. So that sort of says transform y. Transform y. Okay? And you want to go up in the y direction because of the rule. What's going to happen to the heteroscedasticity when you go up in the y direction? Get it better or worse? Worse. A lot worse. Right? So, for instance, if I now... So let me do what the game suggests. Let me plot x versus y squared. Let's see what happens. Right? So I'm going to plot x versus y squared. It's a little bit strong. Straightened it up, but the heteroscedasticity got a lot worse. And I mean a lot worse. Look at the scale here. 8 times 10 to the 10. Right? This is starting to look like national debt. Okay? So these are big numbers, and it's really pulled apart. So I straightened it, but the heteroscedasticity got a lot worse. Okay? So what I'm going to try and do instead is I'm going to try and take x down the ladder and see what I get. So let's plot square root of x versus y, square root of x versus y. And you'll notice that straightened things out a fair bit, but I've still got the heteroscedasticity problem, right? So it was pretty curved, and now it's more or less straight, but still doing that. But now that I'm here, I could transform y down the ladder, and that should fix the heteroscedasticity problem. But this is probably too straight as it is. So what I'd like to do is something kind of weird. Instead of going to square root, I'm going to go to log. In other words, I'm going to pull it too hard so that it curves upwards more vigorously. And then I'm going to transform y to pull it back down and control the heteroscedasticity. So I'm going to go from y to log y. Okay? And that's about as good as I'm going to get. So that's pretty complicated, right? That's a lot of effort. But you can see I can use these basic simple rules to pull this curve around to both straighten it and have its width become uniform. Okay? Now, look, if you're looking at this data for the first time, okay, and you're not going to immediately go log, right? You're going to mess around with it a bit more in order to get it to where I've got it in a couple of minutes, right? Because I already, it's like one of these cooking shows, I already pre-messed with it. I knew what was going to happen by playing around with it before I came here, okay? But that's what life is really like. You have to use the information you have, the knowledge you have around what generally works to move this curve around, and then see if you can combine these different things in order to get the answer that you need. Okay? So straightening scatter plots is a bit of an art. Sometimes it's a matter of transforming one of the variables, and that'll work. In this case, we had to transform both of the variables. Now, the hint that we were going to need to transform both variables came about when we realised that the single solution, transforming one of them, would fix one problem, the straightness, but not the other problem, the heteroscedasticity. Okay? If you've got to fix two problems, you probably have to do two things if the first solution doesn't fix both of them. And that's why we ended up here. Okay? If I put the low S curve through this, and again I'm going to have to leave out the the points that are missing, so log of that and log of that, you can see looks pretty straight. Maybe a tiny hint of a curve to it, although I will say that the data's a bit sparse down this end, so that little bit of pull down here is possibly an edge effect to that point. So I think it's about as straight as you're going to get it for real data. Okay? Now, it turns out if you go and talk to a biologist about birds, they'll tell you a log-log model makes theoretical sense. It's a model for what's called dimorphism. Okay? And so this is an example where the statistician bumbling along, just looking at the data without any sort of external knowledge about birds, says, well, I think log-log fits best, gives you the best characteristics in terms of linearity and in terms of the spread structure. And then the biologist says, oh, log-log, yeah, that's what we do all the time, right? That's our theoretical model for how this stuff works. Everyone hugs, it's all good, right? The data matches up with the theory. So that's kind of what you want. So straightening scatter plots is, well, there's an art to it and there's a science to it, right? I mean, we basically are leveraging the fact that we know how functions affect straight lines, how functions affect curves, right? So we're using that fact. We also know that the curvature of the pattern, we know how strong that needs to be for certain functions to work better than others, right? And so we know this ladder of power idea tells us what functions are stronger than what other functions, and sort of gives you a hint of what to do if your initial attempts either don't bend the curve far enough or bend it too far or whatever. So it gives you some kind of structured way to think about what functions you might deploy in this kind of instance. And again, keep in mind, the reason that we're pursuing so hard this idea of taking data that's got a curve through it and turning it into a straight line is because we know how to fit straight lines. They're dead easy to fit. They're very compact, right? If you can reduce a relationship to a straight line model, you just need an intercept and a slope and you're good to go. And all that comes with that, all the predictions, all of the ability to interpolate particularly and extrapolate mildly. All of these things come with that nice parametric model. Okay? So that's a little bit about what I would call scatterplot straightening and the functions that you might use to do that. All right, now I want to go back and talk a little bit about spread. So I'm going to go back to my original rat data. So I'm just going to read that back in because I got overexcited and overwrote the rat data with the raptor data, so I've got to make sure I go back to the data I had. Right, so I've got my old X and Y back. Okay, so that was my original rat data. And I want to look at the spread characteristics of this, okay? In its current form, because it's got the curve through it, in order to look at the spread, I have to do that thing we talked about where you take your two fingers and the two fingers have to do two things simultaneously, right? They have to keep wide enough apart that you're capturing most of the data, and then they have to move when the data moves, and so you can sort of do that, okay? But look, as anybody who's ever tried to pat their head while rubbing their tummy, doesn't really work too well. Your hands don't like doing two different things. So when I do this, I start to do this. Oh my God, right? Doing two things at once is kind of hard. Tells you something about how, well, frankly, low-tech humans really are. You can do one thing quite well, give us two things to do. Well, if you're male particularly, you're completely stuffed. If you're female, you might have a hope. But, you know, it's not good, right? So this idea of, oh, I've got to move my hand up as the data goes up and at the same time move my fingers apart, that's not going to work as a sustainable way to think about data, is it? Okay? So what we'd like to do really is sort of separate out discussions of location, which is where your finger's basically going, and spread, which is how far apart your fingers are going to be. And this brings us to a discussion of what we call residuals. Okay, so what's a residual? A residual is the difference between a particular data point and what your model for that data says it is. Okay, that's what a residual is. Now, again, you guys are sitting in a third year stats class. Why am I standing here defining residuals? You know what they are. Well, I'll tell you why. I want to make sure you absolutely understand that residuals are a model-dependent construct. You can't have residuals if you don't have a model. Okay? See, it strikes me that when you cover this stuff in first year, we don't really talk about that enough, right? Residuals are a model-dependent construct. People talk about residuals as if they're somehow innate to the data, right? And so people talk glibly about, oh, that point's an outlier because it has a big residual. And they ignore the fact that the residual depends critically on what the model is, okay? The model predicted the point would be here, it was elsewhere, that difference is called the residual, okay? So we're going to come back and talk about that important feature of residuals as we go. I just want to make that clear to start with. Now, for this data, at the moment, I don't know what the hell the curve is. The best I can do at the moment is to put a low S line through it. That's easy to do. Lines low S, XY, and I get that. So that covers the location. That's the model, if you like, in this case. Starts off flat, rises, and heads off the end of the plot there. Okay? So, what are the residuals here? Well, the residuals are what I would get for any individual data point by, say, sticking my mouse on that data point, there it is, and dropping straight down to the line, there it is, and measuring that distance. That's the residual. Okay? Now, what if I had to compute that? What would I do? Well, if I knew the formula for where the line was, I'd be cool, because I'd just take the y that I've got and I'd subtract off the formula for what y would be given x. But I don't have a formula, right? Low S doesn't give me a formula. So I've got to do something a little bit less happy, I guess. I've got to use a function in R. I'll tell you what it is. I'm going to find it down here. Called approx. So what does the approx function do? So let's have a look. I'm just going to go help approx. Okay, so here we go. Help approx. Here it appears. It says return a list of points which linearly interpolate the given data points or a function performing the linear or constant interpolation. Okay? So this is where it's going to help to see what low S is actually doing. So what I'm going to do is this. I'm going to go, okay, I'm going to create an object. I'll just call it temp, TMP, equals low S of x and y. Okay, so what that does is it performs that low S calculation and then stores the output in this thing called TMP. Okay? So it's a list. So if I go names of TMP, it'll tell me what the names of the elements are. It's got two elements, an X element and a Y element. So let's look at TMP $X. Okay? Let's look at TMP $Y. Okay, so this is what low S does. It takes each of the X's, right, and it calculates a Y for it, okay? And you'll notice there are 92 of them, and there were exactly 92 rats. So it calculates for each X in your data a value of Y that is on that curve. So it does that calculation. Now I'm going to plot these, but I'm not going to draw it as a line, I'm just going to draw it as points, right? So I'm just going to plot, I'll just plot XY to start with. Then I'm going to do points, temp $X, temp $Y, okay? PCH equals 16. I want it to be a solid dot. Colour equals red. So this is what's going on underneath low S here. So a tiny little bit of imagination and you see that line, but I haven't produced it as a line. I've simply said, okay, what are the points that are going here, right? And now, if I take that set of points and I join the dots, literally join the dots with little straight lines, that's exactly the low S curve that you see, okay? So if I want to get a residual, I just take the Y value at any particular spot and I want to subtract off basically the linear interpolant of those dots, those red dots. And that's exactly what a prox does. It does a linear interpolation. So if I want to calculate the residuals for this low S curve, I'd go res equals, and I'd go, well, it's Y minus a prox, okay? I give it temp dollars X, temp dollars Y, so that's my low S fit, okay? And then I want the Y component of that. I want the vertical component of that. So these are my residuals. Oh. Y? What's Y? 92. Okay, something's going on here. It's not producing 92 of them. Oh, it's suppressing the zeros. That's very odd. Why is it doing that? Oh, I'm a bit confused suddenly. I think they might have changed some of the output to the approx function. Let me go back and look at this help. So you give it X, give it Y. What's the output? Value. Returns a list with components X and Y in coordinates with interpolate the given points according to the method and rule desired. Sorry? Oh no, because I actually said up here, I said temp is low S of X and Y. So that should have done it. And then temp dollars X had 92 elements and temp dollars Y had 92 elements. The only thing I can think of here is that there's all these zeros which it might be collapsing. Have been pulled out. That's odd. I didn't used to do that in the previous version. All right, bang head on desk. I have to think about that one. Not to worry. All right, let me resolve that and I will report back tomorrow. Don't worry. All things can be solved, but it requires thinking. So I'll have to go back and think about that. All right, leave that one with me. This the exact command worked the last time I did this, so yeah. Not to worry. Okay, well we'll come back to that. We can still get residuals for a parametric fit. That is easy to do. So let's go and have a look at that. So we've got plot X and Y. Okay, there's my original data. We know from all of our messing around that if I take X and log Y, I get something that looks plausibly linear. Okay? And I can fit a straight line to this. All right, so let's go ahead and do that. So I'm going to call it model 1 equals ln of x, log y tilde x. Okay, and I can go AB line, model $1 coef. Whoops, an extra space. So there's my straight line there. Okay. Now, I'm using LM. LM fits a simple straight line using least squares. So I'm going to talk about least squares in a second, because least squares is an interesting story. But fundamentally, what it's doing is it's trying to set a line through the middle of the data, and it does that by minimising an objective function. That objective function is the sum of squared distances of points from that line. Okay? And it goes ahead and fits it. That object, model 1, if I look at it, it's a list. If I look at names of model 1, it's got lots of components. The first one's coefficients. That tells me the intercept and the slope of the line. Its second component's called residuals, right? So if I type residuals of model 1, I get these. Okay, there they all are. Okay? Now if I plot those residuals, if I plot x versus those residuals, I get the following plot. Looks like that. Now, let's think about this plot relative to the previous one. Okay, the previous one was the original data, and now we've got this one. So I'm going to put them side by side. So I'm going to go par mf row equals c side by side, so 1 row, 2 columns, 1, 2. Whoops. 1, 2. Okay, I want to make this surface here a little bit wider than it is tall, so you can see them side by side and it looks kind of sensible. I'm going to go on the left-hand one, where am I typing? The left-hand one, plot x and log y, and on the right-hand one, plot x versus residuals model 1. Okay? Now there are two main differences between these plots. Okay? So the first one, and I haven't got any reference lines on these, so you've got to use your imagination a little bit. Okay? So this one here, you've got a cloud of points. You can see it's drifting up the page more or less linearly. Okay? So you can sort of see this, and you can sort of see the spread characteristics. And again, you can do that two-finger thing where you sort of go, okay, it starts about here, and it drifts up the page. There's no need for my fingers to really change their distance apart. Yeah, it's probably a little bit skinnier in the middle, but not too bad. So we just sort of do that. Okay? Now, one of the consequences of this is the scale goes from here from about 0 up to about 4. And the reason it has to go from 0 to 4 is that when x is low, y is low, and when x is high, y is high. So that isn't really the scale of the data, it's the scale of the relationship between x and y. So the reason I need to go between 0 and 4 is because the data's down here to start with and it ends up there. But it doesn't represent how far my fingers are apart, that moves, right? So it sort of moves. Now this plot here, let's play the same game with this plot here that we just played with the last plot. We're going to start with one finger. I'm going to ignore the spread. Where's this plot going? If I said, where's the location? What's the location doing? Yeah, it's flat, right? It's flat. Now I can show you that, right? If I go lines, low s, x, residuals, model 1, what I should see, pretty flat, right? So in a sense, what I've done is I've taken that original plot, which is sort of going up the page, and I've basically dropped the high ones, left the low ones, and it's now flat. Okay? So I've squashed it. And I've squashed it vertically. I've flattened it, projected it, is the technical mathematical term, right? I've dropped it down, projected it. In other words, I've removed the model. So what's left is residuals. I've taken the data, I've removed the model, data minus model equals residual. Okay? So that's the first thing that's different between these two